When you design a system, such as an aircraft powertrain, it's helpful to try different combinations of components to see which work best in various conditions. You can use the manufacturer-provided specifications and performance characteristics of the components to compute properties and performance characteristics of the integrated system. Using spreadsheet software such as Google Sheets or Microsoft Excel to perform these calculations grants you the ability to update each variable as components, assumptions, and design constraints change. This is known as system modeling. Many designers prefer to build their models in programming languages, such as Fortran, MATLAB, or Python. This may take longer to build at first, but can grow to provide advanced predictive and iterative capabilities in drone design. Spreadsheets are quick, easily accessible, and more people are familiar with their use. Now, we look at a course resource to aid in the powertrain design process. What you're looking at is the Motorbase. Motorbase has been populated with manufacturers' bench testing data for various motors. Make sure to save this file for use for future projects. Each motor in Motorbase is listed by name in the first column. The same motor's performance can be notably different when wound to a different kV, paired with different propellers, or run at a different supply voltage, so these combinations are tested separately. In the motor bench testing, motors equipped with propellers are run through a range of throttle settings, while the resulting current draw, power consumption, thrust, and speed are measured. Each data point in a test is a specific throttle setting, taking up a row of the sheet. There are usually between 4 and 10 throttle settings per test. Motor selection is a common starting point for your system model. While you don't need to use the Motorbase in motor selection, it may be easier and more convenient than leafing through many specifications pages on manufacturers' websites, and you may very easily find the performance characteristics you are looking for. For example, let's try to design a powertrain for a drone with a gross takeoff weight of 4,800 grams or 4.8 kilograms. We divide 4,800 by 4 motors, getting 1,200 grams. So we go to the Motorbase and filter for all motors capable of producing 1,200 grams of thrust. Here it'll be greater than or equal to. We filtered it down to fewer motors than we had in the Motorbase before. We want the 1,200 grams to be the motor's hover thrust because we need some envelope for maneuvering, and we don't want to be operating at the limits of the drone. A good range for hover throttle is around 50 to 60%. Then we can maneuver at 60 to 80% and try to avoid maxing out the motors with the remaining 90 to 100% because these operating regimes are usually less efficient. Our motor and propeller options have been further narrowed. Let's now pick the option with the lowest power consumption within our range of interest. Now remove all the filters, copy the test data you're interested in to a new sheet, and you can begin your design.